Interesting. So I think we can start.
Yeah.
All right. Cool. Hello everyone. Welcome to the Fast Confirmation Rule Workshop. Glad to see you all. Basically, the goal of this workshop is the kind of educational one, just to present the algorithm, go into these complexities, and gather early feedback and facilitate its further development and delivery to the main. So, does it work? Mm-hmm. Oh, yeah. Click here. All right. So today I'll go through the algorithm overview and a little bit the spec overview. Probably somebody already saw the spec on the GitHub. We'll touch some of the complexities of the algorithm and potential implementation challenges. Also cover potential improvements to the algorithm and testing and delivery. A little bit about API as well. So this is going to be kind of like presentation, but feel free to stop me at any point in time to ask questions. I think we'll do this the first part, and the other part just the discussion and follow-ups. I mean, like we'll go through the slides, the first part of this 2 hours, and and do some follow-ups. All right, so the algorithm. So let's start from like the high level from the consumer's perspective. So what we try to deliver, it makes sense to start from the definition of the confirmed block. The confirmed block in the context of this algorithm is safe under synchrony, assuming no more than 25% of total stake is adversarial.
Is the 25% a hard-coded number of the algorithm?
No, it's the maximum number. So
we are reducing the honest validator thing from 67 to 70. Like right now, I think 33% can be adversarial, and now it's like 25.
Yeah, exactly. It can work with 33, but some of the things doesn't look safe. We have been working on the proofs of the safety of this algorithm, and ended up that 25 would be the best. Like the best number for that, because for 33% you have to please Roberto, correct me if I'm wrong, but you have to do some probably more assumptions or whatever, so it's less safe. And I would think that 25% is pretty much enough in terms of like the fraction, like it's already big now.
Okay, and is that like something that like that the users should be configured, like if you want more security or less security, like 0 to 25, or do we just need a single value?
It shouldn't be a single value, but I think it shouldn't be configurable by users. It's more like up to a client implementation. And currently, it's just a parameter in the it's the parameter in the config of the in the mainnet and minimal configuration in the configuration basically.
Okay.
So it's set to 25% as the maximum value, but any client implementation can tweak it. That's
like downwards.
Downwards, yes.
And you said you're working on proofs for proving that 25% is good enough. Is this proofs, like some data related to those proofs, are in the part of specs or not?
That's a good question. I don't know. Actually, it's just like for now, it's our understanding that like it's our perception that like our view that 25% is enough. I believe we haven't checked the rules yet. Maybe Francesca, you know something more about it. Guys. Sure.
Okay.
All right.
With the current algorithm, like if you have more than 25%, the adversary can more easily prevent confirmation. Then you don't see anything being confirmed, and now you don't know whether there is a network problem, whether the adversary is just not participating and preventing blocks from being confirmed. And like if you set the threshold higher, actually the adversary can prevent confirmation with a lower threshold because like you expect more attestations, and so now the adversary can be even smaller than 25% and still prevent confirmation.
Okay.
That's
So
the problem.
yeah, thanks a lot, Roberto. So the synchrony assumption that we made is basically means that the votes cast by honest validators will reach out to all other honest validators by the end of the same slot. So that's for the synchrony part. Right, let's move on. So the performance of the algorithm that we have measured on the tech proof of concept implementation. This is the data from the mainnet. Yeah, it's pretty good. So in 3 slots, you have 99.5% blocks confirmed. Yeah, this delay is in second, but basically it's like 12 seconds is 1 slot, 24 seconds is 2 slot, and so forth. The problem here, why do we not confirm a block at the beginning of the next slot all the time is basically because there are late blocks that might gain less attestations than it is required to confirm a block, or because of empty slots sitting the block. We will cover empty slots in this simulation later on. The late blocks part as well will be covered. So yeah, this is the measurement of the currently proposed algorithm. This is what we can do, which is good. All right, so the illustration, this is the kind of like my mental model of the fast confirmation rule. Yeah, there is like something stable surface in terms of like a reliable block, which is close to the head that we provide to consumer. There is a Gasper that does not by default provide that, and there is the fast confirmation rule to fill the gaps of Gasper to do this work. So from this illustration, we can conclude that basically confirmation rule is at top of the core protocol. It's not a part of the core protocol. It works at top of it, and also like it's quite sophisticated algorithm in some sense to fill all the gaps of the Gasper. Of course, Gasper can provide finality. It's pretty stable. It's also pretty stable surface. But here we're speaking about something that is much closer to the head than the finalized block. All right. So how do we run the algorithm at the very high level? We do run it iteratively every slot. At the beginning of every slot, so we attempt to confirm the most recent block that belongs to the canonical chain. So what does it mean actually? Suppose that in slot n we have confirmed block B. Then in slot n+1 we will start from block B as a confirmed one. So the algorithm remembers what the most recent confirmed block is and attempt to move forward. So we will confirm block B1. For instance, in slot n+2, we failed to confirm B2 because probably this block came too late and did not attract enough votes. And yeah, we tried to confirm B2 and we failed. And then in slot n+3, if there are more attestations for B2 will come, we will or more attestations will come, or it just will be a very good participation in the slot of block B3. We will be able to confirm two blocks. So it's basically we start. So the main thing here from this slide is basically we start at what we have finished with during the previous slot and forward as much as we can. So it's an iterative execution, which is also like an upside of this approach, of this algorithm. Then the question, where do we start? So suppose your node just have a startup. It does not know anything about the confirmed block. And by default, it will use the finalized block as the confirmed one. But we need a safe starting point to start confirming blocks that are closer to the head. And there is a category of blocks that we that are safe to start with. This is the basically the unrealized justified checkpoint root block. And we actually wait for the unrealized justified checkpoint. Yeah, we start at the epoch boundary at the very beginning of the epoch. We check if we need to start, if we're kind of like if our confirmed block is way behind than what it could be. And if we find like the unrealized justified checkpoint that we have observed at the beginning of the last slot of the previous epoch, and this unrealized justified checkpoint is from the previous epoch, so then we can use it as a safe starting point. This is because basically this unrealized justified checkpoint that we observed at the beginning of the last slot of the previous epoch, now, since we turned into a new epoch, becomes realized for all honest. Assuming synchrony, it becomes realized for realized justified checkpoint for all honest nodes and for all honest validators. And moreover, it's the greatest justified checkpoint possible because it's from the previous.
Is this based on the Python spec, or is this based like what is the implementation that this code is referring to?
It's from the spec.
Okay.
It's from the PR. It's just kind of like mix of pseudocode and English, so it's like basically.
No, it's okay. I mean, in Nimbus, we only store one checkpoint, and like after we realized the checkpoint, we forgot about the historical unrealized one.
Oh.
Like we just override it. So in our case, this is essentially just a regular realized justified check because we realize everything that's unrealized.
Not exactly, because you also need to. You also have to check that this unrealized justified checkpoint has been observed by you. It has been in your local view a slot ago.
Yeah. I'll have to check that.
Yeah, of course. So it's a bit tricky. This a slot ago observation is required because we want every honest node to ensure that every honest node in the network also see it.
Yeah.
And which is assuming synchrony will be the case. So what should I say else about? Okay. So when we start, we find this safe checkpoint to start with, and also in the same run, the algorithm will attempt to confirm as much as it can. So starting from this unrealized justified checkpoint, moving towards the head of canonical chain. So that's basically about starting point. Yeah, and by default, I already said that, but by default, it will be a finalized block, like as a confirmed one. Right. Yeah, and also this brief epoch unrealized justified checkpoint is the new variable in the store. Yeah.
The chain is not finalizing. You have no starting points. If the chain is really unhealthy. It's a start epoch boundary where this unrealized justified checkpoint is the previous epoch.
Yeah.
You don't have enough votes, then you aren't confirming. Is that right?
So you mean that if chain is not finalizing, but you see the starting point, is it safe to start from it?
And if you don't see the starting point.
If you don't see the starting point, then the confirmed block basically was the finalized one. If you don't see it,
okay.
If you cannot confirm anything, then you just wait for the network to get recovered.
And if I could add something to that, like just as a general observation, like actually it would be very unsafe under low participation conditions to confirm things. It's not like a general rule, but like in our protocol, it happens to be the case that in under certain like low participation conditions, like really any kind of weird reorgs can happen. So it's basically impossible to have a confirmation rule that works under those conditions in our protocol.
Right. Let's move on. Yeah, so I forgot to mention that the confirmation rule deals with LMD Ghost and with the FFG as well. So deals with Casper. And yeah, let's just dive deeper into the LMD Ghost part. Then we will cover the FFG part as well. So at the high level, if we want to confirm block Bn plus 3, for instance, here, it's yeah, we will have to check that every ancestor of this block and this block itself satisfies LMD Ghost safety condition. So we will do this check for all of that blocks. And at the high level, what we are looking for a as a confirmed branch of the block tree. We are looking for the branch of the block tree that under synchrony and our adversarial fraction assumption will remain canonical starting from this time onwards, regardless of what will happen in the future, of how validators will vote, what votes will come into the future, what like adversarial behavior will be, or whatever, because we expect that basically honest validators will keep voting on that branch. So here, this is the simplified formula of the safety indicator on the top, where S of BI is basically the support of the block. It's the total weight of the votes that we have observed in the support of block BI. And on the right is the safety indicator threshold, where WI is the maximum weight of all committees that can vote in the support, or again in the support of block BI, or in the support of a conflicting block to conflicting with BI. The beta is basically the adversarial fraction, and the PB is the proposer boost. So if we simplify this formula and remove the proposer boost and suppose that we have zero adversary, basically we will see this very simple version where the block is considered LMD Ghost safe once it attracts more than a half of the maximum possible weight that it basically can gain. In this case, yeah, we can be sure that under synchrony, all honest validators in the future will keep voting in favor in the support of this block, and this safety indicator inequality will hold all the time starting from now. So the block will never leave the canonical chain, and we do this check for every ancestor of the block. So that's basically the LMD Ghost plot.
So in this diagram, this BN is last confirmed block or last justified?
BN?
Oh,
it's just it's just some confirmed block. Like this blue this subtree, like this branch of the tree that's highlighted in blue is the one that we are looking for, the one that is confirmed based. And for each of these blocks, this check must pass.
What is the if some validators are offline on top of the adversarial state, the weight only counts the actual votes, right?
Yeah.
So if I have a slot with low participation, and the next one maybe if the network changes from one slot to the next, either from high to low or from low to high, how does that interact with this formula?
So if you confirm something already, it will stay confirmed. But if the network participation drops significantly and some mess happen in the network, this will mean that the synchrony assumption is broken. Yeah, and
because the W just scales to a because the W, like the safety indicator threshold, depends on the online percentage.
Yeah, exactly.
Nice.
Yeah, and
No,
yeah, if
W is the entire committee. Is independent of the participation.
yeah, but support is dependent on participation.
Yeah, no,
and
but
so on.
the support, not the W though. The support is dependent, but the W is the weight of the committee, regardless of how many are online.
That's not like based on the actual. Okay,
Okay. Yeah, so like if you look at the one, the simplified one below, on the right, it's always gonna be this fixed based on what the committee size is. It's just like the total amount of weight evaluation. But on the left, it's just the actual votes that you see.
I see.
So if there's no participation, you will just not have the application.
Oh, sorry, I misunderstood the question. I thought you were asking like what will happen is basically if we don't see enough votes. We'll
Yeah,
just
yeah.
not-
Now then it makes sense. I thought like W is weight, like in the four choice debug point. I think weight means the actual vote and not like the weight of the.
Oh, I see what you mean. Okay, yeah.
I mean a different term.
Yeah, that's the maximum weight. All right.
maximum
Yeah.
capital W, right? Yeah, then it makes sense. Thanks.
So what we have here is we are trying to confirm block B11. And we suppose that adversary is basically adversarial fraction is 20% for simplicity. And the maximum weight of each slot committee is 100. So we are in the slot after block B13. And here to confirm B11, we basically need to take into account the slot of block B11 and the votes from the slot of block B11 and the votes from the slot of block B13, which is like we have 80 and 85 score respectively. So the total is 165, and we have and the weight is 200 because there are two committees. Yeah, also, so we just basically pass these numbers to the formula, and we get that the threshold is 160. Which is, and the actual weight is greater than this threshold, which means that B11 will be confirmed. Also, pay attention to that the B13 has a proposer boost value. So it's like it's a timer blocked, but this value is not, is discounted from the formula. So we discount this weight from the B11 support. Yeah, it has 165 because the B13 is the descendant of B11, and its weight also adds up to the B11. So that's basically the how the computation happens. Actually, the formula of the threshold is more involved. Yeah, but these are the main components of it. Move on. All right. Yeah, let's cover a bit the empty slot stuff. The empty slot case. As I mentioned before, we have to W. So we have to basically count to check if the block is confirmed. If there is enough support with respect to the weight of all committees that can vote in the support or against this in the support of the block in question or in the support of a block conflicting to that one. In this case, there is a slot K which has no block, which is empty slot. And in our computations, we have to take this also into account because during the slot K, there can be votes not in the support of block P10, which is the parent of P11, but in the support of the block conflicting this one. And even if we have a perfect participation, which is illustrated here, we will not be able to confirm this block immediately because there will be not enough support to outweigh this maximum weight, which is 200 in this case as well. Yeah, because 100 from the slot will be 11, and the other 100 is from the empty slot. So we handle this situation. This is one of the complexities of the algorithm. We handle this situation in the following way. We basically count the honest support of the parent block during the slot K. So here you can see that the total support of the parent block during the empty slots was 100. So all values voted in favor of that. To compute the honest support, we need to get the support of the parent block strictly from slot K, subtract the potential adversarial walls from that. Discount this honest support of the parent block from the safety threshold on the right. And this basically, in this case, the adversary is like 10%. We can confirm B11 at the next slot. But in the case of 25%, it will still not be possible. So empty slots really delays the confirmation. But by doing this trick on this slide, the delay is kind of reduced. All right, something similar happens with blocks as well.
With what?
Late blocks. Yeah.
And this go negative, like when the support is.
Oh yeah. Of course it can, but
when H is negative.
Yeah.
I think, but
it can go negative, but
maybe not. Is just the current committee. Like with Hector, we had this single attestation, right? Where in theory, someone that's not in the committee can make a valid attestation message that still has a valid signature. We are discarding those.
What's the situation?
Like with the single attestation type that we have in Hector, anyone can make any attestation at any slot. They are still slashable, but I think they are not countable. They're not in the committee for that slot. Just yeah. But the network type has a validator index instead of like a bit mask into the committee.
Oh, you mean like with the single attestation? I see.
Yeah. Very much.
All right. So should we move on?
Yes.
All right. So this is like the LND ghost. As I mentioned, the formula is more involved. This H, this honest support cannot outweigh the W actually. Yeah, but anyway, so there is in the explainer document that Luca has recently shared this formula outlined in all the details it has. It's more, there are a bit more details in that. So FFG high level. So what the fast confirmation rule has to deal with FFG is basically the main point is we have suppose that we have LND confirmed some block, but you're all familiar with these checks in the get hat filtering, and basically the algorithm ensures that the confirmed block, the LND confirmed block, is not gonna get filtered out during current and next epoch, because it can simply filters out and it becomes non-canonical block. Yeah, that's what the FFG part of the algorithm deals with. And if the block is not filtered out during current and next epochs, the next epoch checkpoint will be, and assuming synchrony, the next epoch checkpoint will be justified, and this justification will be realized 2 epochs after. So this block will have a justified checkpoint, which is a descendant of the confirmed block. So it will then, from that time, it will remain canonical, and we will not need to care about this filtering anymore, because it will remain in the canonical chain from the filtering perspective. And also, the algorithm does these two checks, which is will checkpoint be justified for current epoch blocks. A similar check that no conflicting checkpoint can be justified for previous epoch blocks. This is like the check to ensure that the checkpoint of the current epoch will be justified given the synchrony assumption and given the votes that we have already observed. Because yeah, if this check would not pass, then we cannot say that the block is safe, because let's just imagine if we cannot justify the checkpoint from the epoch where this block is from, then basically potentially something conflicting can be justified, and will mean that the block, it just means that the block is not safe to use, it's not confirmed. So we do these checks, kind of like looking a bit into the future with the votes that we already have, like supposedly in the middle of the epoch. We know that how much votes can be adversarial from that support, and we also know how much slots left to vote. We have this adversarial threshold, and we can assume that all honest will support this checkpoint. This is basically, and if the sum of all actual and potential support is higher than the justification threshold, then basically this check passes. So this is how it kind of works. Yeah, so filtering checks. I don't want to go through this now. It's just basically more for illustrations here, but there is a quite sophisticated logic to ensure that that block is not gonna get filtered out for previous epoch blocks when we confirm previous epoch blocks and when we confirm current epoch blocks. So if there will be need, we will get back to these slides. Yeah. All right. So failures. How the algorithm can failure. The first failure is basically the confirmed block appeared to be not part of canonical chain anymore. So this is the safety failure. It must never happen if the assumptions hold, but that could happen. In this case, what we do, we basically revert to a finalized block. So we explicitly say that this block is not safe anymore as a confirmed one, and we have to do revert. The other two failures, the second one is related to reconfirmation. We will cover reconfirmation later. The third one is suppose that we returned into a new epoch, and we see that the confirmed block is base. Yeah, first of all, there must be something bad happening in the network, so the assumption again is broken, because otherwise it should not happen. It should never happen. And in this case, we just stop confirming, because it is difficult to show that the block is not going to get filtered out, that it will be safe to use. So this kind of like this, and the failure mode for all these three is basically revert to finalized block. For the first one, it makes sense to revert, but for the second and third cases, probably not. So yeah, we'll cover this later. Like this could be one of the improvements of thinking about the failure mode for the third and the second, for the third and the second case, because in this case, basically the block remains canonical.
So in the third case, we would have to wait until finality is restored, and then the algorithm would start working.
We will have to wait for the starting condition. So we basically use it as a restart as well.
Yeah, but the start is from finalized, right?
No. We will revert to finalized, and we will wait for this starting point again.
Why to finalize? Why not justify? Well,
because justified is unsafe, can be unsafe.
Yeah, justified by design can be.
Yeah, it can be real. Yeah.
So because like you only have like 2 epochs that we have to consider, that also is like an upper bound for the implementation like runtime that this stuff needs. Like, because if the starting point, like if the last confirmed is too long ago,
Yeah.
We only have to look at most at 2 full epochs of blocks.
In the implementation.
Yeah.
Yeah.
So that's good. Yeah.
Yeah, that's
So
kind of limitation on the complexity, on the data complexity.
Yeah, that's good. So even if it's like quadratic or like whatever the algorithm is.
Yeah, it's too heavy. Yeah, that's the positive side. Yeah, so the algorithm basically. Yeah, this is the failures.
I
Most
think theoretically,
when you go
I think that
from
theoretically, perhaps we could, in the last case, perhaps we have ways to cope with the confirmed block being from 2 epochs ago. Like, it's not in the current algorithm, but we thought of possible ways. Like if we think that in the last scenario, we don't want to revert necessarily to the finalized block, perhaps there is something we can do to the algorithm to cope with the confirmed block being from 2 epochs ago.
By coping, you mean like not to revert it, but not probably and not confirming until the certain point, right?
Yeah, and determining that it's still safe. Like,
Yeah.
Oh yeah. Like because the
Yeah.
third condition can like regularly, right? Like that can happen like when finality is broken.
Oh, yeah. Not on the mainnet, right?
I mean
Theoretical.
yeah.
Yeah, but on Holosky it would happen. Definitely.
Yeah, Holesky was like a situation where like a justified checkpoint was like based on an invalid block.
Yeah. Right. So what Roberto is saying, basically, we will stop confirming,
Yeah,
but we probably can find some conditions to check that this block is still safe to rely on, but we just stop confirming.
Yeah, that makes sense. Like for infrastructure providers, you don't want the safe to go back.
Yes, right. But there is a failure mode when you have to go back finalized. But it's quite like
Yeah, like the first two, but like the third one, I think.
The second one probably can. The second and the third one is more kind of liveness issues, or maybe safety as well. But we will try to find a way to to understand whether we can still keep them.
Yeah, so this is definitely conservative and safe. The first one is there a reason why we don't just go to the parent block, or like why is everything not safe?
Oh, that's a good question. Yeah, it's a good point. Interesting. I don't know. I haven't thought about it.
One way you think about it is that if the confirmed block was reordered, it means that the assumptions were violated. So in principle, no confirmation is like known to be safe, but like I don't know, it could also just be fine. I think it would be fine to just go to the latest confirmed thing that is still canonical.
Yeah. All right, that's a good point.
Yeah, makes sense.
Okay.
I was just going to ask, from like a user perspective, from the time of going to confirm to a reverted finalized block, like how many seconds or minutes or whatever would pass
From the confirmed to back. Like how many in terms of like really physical? Like
I guess
time?
would a user like have a sense of, okay, this has been finalized, and then moments later it would just the transaction would fail and it would revert, or would it be minutes later? Would they?
It depends on the network condition, basically. But we will. Yeah, it depends on the network pretty much. So if we have something bad happens, if we lose finality and some mess happens that the block is revolved, yeah, it can happen like, I don't know, maybe in minutes or in a couple of epochs or during one epoch. Yeah, but it's very unlikely. I mean, At least we haven't seen yet the accident on the mainnet that would lead us to rolling back to finality.
We've had like non-finality on mainnet back when Erigon started the Kaplan node without testing it on testnet, and it released very old stuff.
Right, but I believe that the participation didn't drop enough to stop confirming. Maybe
It's
I'm
not
wrong.
finality.
Yeah, right.
But yeah, this one is 75.
No, 75. You're right. Yeah,
So
yeah.
finality is less than.
How many epochs of non-finality we had by then?
I
Like
have
2
to
epochs?
look it up. It's like a couple of years ago.
Yeah.
And then that was a scary one. Like an EL that like it was like a different layer that rocked us there.
Yeah. Okay. So that's the algorithm. This is a pseudocode. Like what's on the left is the get latest confirmed here. It's basically see this. Yeah, this function is the starting point. What's on the right is basically this function that looks for the most recent confirmed block along the canonical chain. And we have a safety proof for this version of algorithm, or this algorithm, that basically the proof of safety that the output of this algorithm, that the output block is basically safe to use, given the assumptions. Okay. What's that?
To read about like Ethereum finality loss, the website is called Solana Floor. So Solana reports on Ethereum like we are shitting on them, they are shitting.
Oh, that makes sense for Solana.
47 missing blocks. Delays. This was the promotion boost. This was the 2023 one. We had like 2 days, 4 epochs, and 9 epochs.
9 epochs.
Yeah, like they turned it on and it was 4 epochs on finality. Then it like shut down everything, and then they turned it on again and it was 9 epochs.
Okay.
Because we didn't know what it is.
All right. So then we would be in a situation number 3.
Yeah.
You're that likely.
So I mean, in that situation, probably just staying.
Yeah.
What we saved, because there was no branching. It was just lot of finality.
Right. Yeah. It's one of the potential approaches.
Yeah. I mean, whatever.
All right. So the algorithm. Yeah. Let's move to the spec. We'll go over the spec. There is a PR to the spec, so it's just basically excerpts from that PR. So what's in the PR? Basically, one more kind of similar to the fork choice handlers. One more handler specific to the bus confirmation rule. It's more or less, it's kind of artificial handler, but what it basically tries to show is that the confirmation rule should be run at the slot boundary, at the new slot, at the start of new slot, after attestations of the previous slot has been applied. So to take them into account, it has been applied to the fork choice. So if your client runs the fork choice for slot n+1 at 11.5 or whatever seconds into slot n, basically this would be the moment where you can also run this code of the confirmation rule. But bear in mind that basically the confirmation rule also uses the current slot, which borrows from the store. So it should be also kind of like the next one, the next slot, if you kind of run it before the next slot action. What it does, it runs the algorithm, stores the confirmed route, and also updates a couple of variables that also are added to the store and used by the algorithm. So these two used by the algorithm. The pre-people can realize just flashing point you already saw. The pre-slot head is basically the head of the observed at the beginning of the previous slot. Right. So the get next, the get latest confirmed is basically the entry point. It has 3 blocks. Failure handling, we covered that. This is where we revert finalized. Then the starting point, we also covered that. This is where we start or do a restart, whatever. Yeah, and then basically advance the confirmed block towards the head as much as. Yeah, this find lane is confirmed the standard, quite sophisticated one. These ifs are very complicated. So the blue lines, this is basically where the algorithm deals with Casper FFG. Like this, the blue line, the blocks highlighted by blue vertical lines, and the green lines is the LNT goes part. The method is called isOneConfirmed, which basically checks the support and compares it to the threshold. And yeah, if this check passed, then this block is on POC. So basically, this is a movement from the previous confirmed block towards the head. Overall each canonical route and doing all these checks. Yeah, sure. All right. How much time? Please. Let's probably like finish this, right? And do a break of complexities. Yeah, maybe interesting part. So now it's time to talk about reconfirmation. Which I mentioned it before. This is, Roberto, please correct me if I'm wrong, this is more a theoretical thing than a practical one, but also, yeah, kind of theoretical challenge. So what we have to do is basically at every epoch boundary, we have to run isOneConfirmed, like check that the blocks are still safe. The blocks from the previous epoch, not like, yeah. So all, yeah, this is quite intense check. So we basically reconfirm. We do not do the filtering checks again, but we do the those safe checks.
This one is not bounded, right?
It's bounded.
I mean finalized.
No. It's only for the previous epoch.
Okay.
Just for the previous epoch.
For each confirmed block. Okay, yeah.
Yes. So this is required to reset the global stabilization time. If we don't do this operation, the global stabilization time we will have to assume it to start from the certain point, which is like, can be, I don't know, 6 months ago, year ago, whatever. So you start at some point and you have to assume that global stabilization time starts there as well. But by doing this exercise, we are resetting it. This is why it's like in practice, it's probably, practically speaking, I don't know, Roberto, if you want to elaborate on that.
No, probably the only thing to add is what is global stabilization time is the point from which we assume that the network is good, essentially. And if we don't run this check, our assumption is that the network has been good since the time we started. Since the time we hit the restart, the condition to restart the confirmation, which, as Mikhail said, could be 6 months ago. Yeah, and I think as Mikhail was about to say, probably in practice, this is not. I mean, we come up with counterexample where if you don't do this and GST is actually and basically GST is older than 2 epochs. Sorry, is more recent than 2 epochs ago. The safe block is not safe anymore, but these counterexample are very contrived. So it's probably very unlikely in practice that if we don't run this check, we have any problem. But yeah, at this point, from a theoretical point of view, we need this.
Wait. Small one, no proposer boost. So the support of a block, the score of a block must be like that we check, must be with the discounted proposer boost value, which is not the case for the fork choice implementation, where basically in plot array weights count with proposer boost. I believe, yeah, it depends. It's implementation dependent, but something to bear in mind. So you can run the confirmation rule at the point where proposer boost is zeroed, right? So there is a point in time, but yeah. But the spec does not have it, so it's a tweak that probably you have to do in the
Yeah,
fork choice.
either we can record like the scores without the proposer boost and then like synthetically add it while computing it because it's only on the head, right?
Yeah, it's on.
Yeah, so just it probably like the other one, the hook, the new hook, that one has to be called like the auto attestations hook. Why is that a separate one compared to like the on tick? Like
Yeah.
we just put it in there.
We can. You
I
mean
mean,
this
it's not
one?
the same thing, I guess, because like if there is a lag spec and you have like an empty slot, we call it on attestations twice. Or, like, is it called once per slot?
Yeah, once per slot, and per empty slot as well. Should call.
So even if you receive no attestation, there is like this on slot after attestations apply.
Oh, but you don't know if you receive no attestations, right?
Yeah. So essentially, if I call this within on tick at the start before I update the time, it should be the same.
Before you update it, what? Sorry.
Before I update the time to the next slot.
After moving to the next slot, and after attestations applied from the previous slot, this slot must run.
Like start of the next slot or
Yeah.
end of the previous slot?
Basically, start of every slot.
Yeah. So time is already advanced. Like
Yes.
And the attestations applied is referring to previous slots attestation.
Yes, exactly.
What happens if I receive an attestation after, like, there is like this clock, P2P gossip.
You mean you receive attestation from the previous slot after that?
Yes, after I already called.
So
it just doesn't. Maybe it has an effect on the reconfirmations, or
no, it should not. Yeah, you will run this in the next slot, which will take into account that late attestation.
Okay, so I can call this. It doesn't matter. Like if I call this too often, it's also okay.
Yes, it should be okay. Yeah.
Okay, so as long as I call it at least once per slot, it's fine.
Yeah.
Okay.
And also, yeah, there is the slot hat, which is that you record the unrealized justified checkpoint in the slot head at the beginning of the slot. This is important.
Yeah. Okay.
This is because of the synchrony. If you call it too late, say like 2 seconds before the next slot starts, there will be not enough, like the 2 seconds will be not enough to ensure that all the honest validators have seen this unrealized justified checkpoint, for instance. It matters. So these two must be recorded at the beginning of the slot, but the algorithm can, probably be triggered.
Maybe after earlier slot attestations applied would be important.
Yeah,
After
maybe.
that,
Yeah, but there is a description in the PR like
Okay.
of this. Yeah, but all right. Yeah, see, the name might be misleading. Why not put this to the on tick? I just don't want this to. I try to make it as much separated from the fork choice because it's not the core protocol. It's on top. So the logic.
I see. Okay. Yeah. But in the end, it still lives in proto array. And back then we also had to change the filter rules to support it in the
No.
core product.
No,
There was something that we had to do.
no, you don't have to change filter. You
No,
don't
no,
have
we
to
had
change.
we had like in the past there were like two changes, like one for the
That's already been done. It went
Yeah,
into
yeah.
a past fork.
But we
The-
already did it, but it was specifically for fast configuration rule to prepare for it.
I
Did it work
don't
for-
think so. What was the change you're referring to?
To the filtering rules. We changed the filtering rules to be weaker.
Yes.
All right, but was it like because of the fast confirmations?
That was one reason. Also, in practice, also reduce the risk of reorgs.
Yeah.
By making the filtering rules weaker. So there were two.
Yeah, it was January. I remember.
Okay.
But the motivation was not.
Oh, I didn't know that.
Can you add this into specs as well as a node?
Sorry?
Non-proposal rules into the specs as a node?
Yeah, there is like basically this attestation score function means that it's just attestation score. It's like in the spec. As a node, yeah, okay. Yeah.
Just to highlight that in like discounting the proposal.
Yeah, okay. The next complexity is that the algorithm, the current version of the algorithm uses the committee shuffling.
It's fine.
That's fine. Okay.
Shuffling is very trivial to compute because you just pretend that the validators that have not been activated yet don't exist.
Mm,
And then you can act or like from the execution payload that break red out to compute the red now. And you don't have to reconstruct the state in implement.
okay. So the shuffling is required for the previous and the current epoch. So if you confirm a block from the previous epoch shuffling will be required. And same for the current epoch. It's used in places like one is reduced adversarial threshold by a fraction of equivocating validators, but we need to know from which committees those validators are. So yeah, this can be done because we can do this because we assume that honest never equivocate. And random equivocation, like because of the misconfiguration of an honest node, should not affect this much. This is more for equivocations of many validators. All right, so mass slashing. The next one is the next place where shuffling is used is to compute the support of the parent block, where we try to recover the empty slot case. But there is an alternative to that. So why do we need shuffling here? Is because we need we need a support of the parent block strictly from the empty slot committees. So this is the algorithm uses shuffling for that, but implementation may, if it has a slot, like it may use attestation slots to basically filter out all the irrelevant votes. So you have slot and you have a block root, so you can basically compute that support without shuffling alternative. But for simplicity, it's just use shuffle.
That's the justified total balance. Like I remember justified total balance. I have to remember.
Justified, like the balance distribution, you mean?
Yeah, like the total justified balance in the stock. Was that in the old specs or?
Oh no. Yeah, not total justified balance. Oh, okay. So we will cover balances in the next. So different states, or to be specific, different balance distributions are used by the algorithm. So the pre-epoch unrealized justified checkpoint state is used for is one confirmed, like for the LMD ghost check. And this checkpoint might be either from the previous epoch or from 2 epochs ago, and it not necessarily matches the justified checkpoint. The justified checkpoint is the one that's used by proto-array. So basically, the balance distribution can be different here. And also, we use current epoch checkpoint state by these two functions, will checkpoint be justified, and the other one. which is similar, which does the same computation but treats them differently. So basically, two states or three potential states from the previous epoch, from maybe from the 2 epochs ago, and the current epoch 1. So 3 states that this algorithm can use. Relies on.
So I guess to what extent is this bounded? Like which aspects of the state? So Ethan is talking about, for example, the total so just try to say balance for example, but as a specific subset of the state in one of these circumstances which is used. And I guess my question is there a theoretically justified way to say in all of these, or is this something that might actually have to be like, are there circumstances in which, at least for some of these, one needs an actual full state, or what's
just balance distribution, not the full state, I believe. Like not balance distributions, but also the what validators are active. So basically validators, validatory records, validator set is what you need for this computation.
But those are accessible from even a current head. I mean, like you can see what validators would have been active during a particular state.
Yeah, but the algorithm requires it to be like not from the current head perspective, but from what was some time ago. Some cases.
From the
from 2 epochs ago, from an epoch ago, or from 2 epochs ago. In most of the cases on the mainnet, this first case, the balance distribution that we use will be from the justified checkpoint. In most of the cases, but sometimes it can be different. Like say the justified checkpoint you have is like I don't know, from the previous epoch, but you have to use the state from the balance distributions from the state which is 2 epochs ago, which is older.
But okay, but this is sort of what I'm getting at as a little this distinction, particularly between the balance distribution, which is one very specific part, and the state in general. Like, and that's exactly the distinction I'm trying to get at here. Like, is this how likely is it that a broader set of requirements would sort of leak into the algorithm, so to say?
How the broader set of requirements
of this state. The key point is states are expensive. States are very expensive to keep.
Yeah.
And so the question is I'll be a little more pointed than right. My concern is if it's written, and as the algorithm spec is currently written, it is written in a way which sort of assumes access to the state, even though it uses a very specific part of the state, which is significantly more cacheable, computable, as Ethan is getting at, as well. So, but because it's written sort of naively in terms of just access the state, it's sort of, even if right now the algorithm in fact is sort of safe, more or less, to not keep reconstructing old states. Relatively minor changes in the algorithm might trigger such a requirement, right? Or because they would look almost the same. Because it just assumes it has a state, so you have to act. So my question is, how feasible, and maybe the most pointed version is, how feasible is it to modify the phrasing of the algorithm to make it very clear what the bounds of the abstractions are, what the so that it basically an expensive modification looks expensive. There's no accidents that can happen here.
Yeah. I don't know. Maybe we just can outline, highlight what's used there, what state is used there, and the other question probably that is reasonable: can we use justified checkpoint state all the time, or at least this is one confirmed? Probably we can, but there can be situations where where we have to use like, yeah, well, if we want the algorithm to work as it's designed, as it's supposed to be, and then we have to use the different checkpoint, different to the justified checkpoint. How to deal with these cases? Maybe the implementation can see that, okay, we use the justified checkpoint whenever it matches the one that we want, because we use the balance distribution from the justified checkpoint because we have this in the proto-array, right? But when it deviates when they're different, we do the expensive computation. I don't know. Maybe that's the way to deal with this. But the safety, the proof of the safety of the algorithm, it relies on the fact that we will use like a specific checkpoint, which is not necessarily justified.
I guess the question, but what information, what specific information is used from that is the key for me, though. Like I understand it has to come from specific checkpoints depending on the circumstance. But it's an extremely different scenario to say one just needs a general purpose access to the state, period, done, or one needs access to a balance distribution, or one actually needs access to a shuffling, or one that is the main. And what I would ideally ask is if has specified the algorithm could be more and proof to the extent relevant could be more explicit about the subsets of the historical states that it needs precisely for the purpose of saying right now, if semi-accidentally or intentionally, either way, if right now, in fact, it doesn't tend to need to reconstruct the state, even in the quote unquote expensive case, because one can do clever things with this. If it's edit distance 1 away from oops, not anymore, now you have to go and reconstruct the state for real. Like that's what I would like to avoid.
Oh, I see. Okay. Actually, yeah.
So you mean like instead of passing the exact state, we should pass the only the fields which.
For example, that's yeah.
Yeah, but I would rather how currently spec out. It's the balance. It's this state that we use for the balance is called balance source. The other one is called the shuffling source. It's basically variable names, but this is how the algorithm tries to distinguish the two. But those are like deep inside of those functions. Like we take them from the store in the spec. What could be done probably is just you pass this explicitly to the algorithm function. Also, we have this for the source of shuffling. That this state is used for the shuffling, so you can substitute it with the shuffle with the cache.
That's kind of what.
Okay. Yeah, that's probably like let's just discuss it in the PR.
Sure. All right.
All right. We're almost done. Okay, FFG support of current epoch checkpoints. One of the things, so we basically need to compute the actual support of the current epoch checkpoint. And what the algorithm does, it uses LND ghost votes to do this computation. It's not goes through all the potential blocks, through the entire block tree, scanning for how many votes, like whether this how many validators voted in the support of this checkpoint. This is expensive, so we use basically the Fock choice data to derive this information. And there is one of the challenges here is that LND ghost votes, they only have a block root, but the checkpoint is the block root and epoch pair. And in the case when the first slot of epoch is the empty one, and the checkpoint block is from the previous epoch. The computation needs to sort out the votes that supported that block in the previous epoch. So it basically requires the epoch of every vote requires to be there and filters out votes by this epoch. This is not the case for the proto-array as far as I'm concerned. So it's just like it depends on implementation as well, but this might be something to think about. So you basically
Can you make sure that when you make the tests, or if someone, I don't know who is making the tests, or if they already exist, but can we make sure that they cover both the Python implementation and also proto-array implementations exhaustively, like more or less? I know like it's hard to measure, but
that's a good point.
I can help you getting like coverage from the if that helps you in some way. But
yeah, that's interesting. Yeah, let's talk about testing maybe later. So guys, do you want to so yeah, and so the block subtree on the positive side, as Ethan already kind of covered a bit, we know that the confirmed block is never older than 2 epochs, or at least if we have this failure mode that where it's older than 2 epochs, we just stop confirming, and we know that it never reverts back, except for the revert to finalized case. So it means that basically once you confirm something, you can wipe. If you do some if there is a need for some optimization and storing some data to run this algorithm faster, yeah, it's great that it's pretty much bounded in terms of data complexity. So if you confirm something, you can wipe out all the previous blocks data, and what you keep is basically a subtree. You keep this information for a subtree that is rooted to the most recent confirmed block.
Is there something that we have to persist across restarts of the node, or is that like
no? So if you restart a node, you are looking for the next starting point.
Okay, so it just starts again and finalized on a restart.
Yeah.
So maybe that revert to finalized is not even an edge case for like a node operator or an infrastructure provider, because like when they restart a node, it also jumps there.
Yeah, that's also a good point. I know how to handle this restart properly, right? Because you don't want this to happen. Because
you don't want to have, you don't want it to happen, but like if it happens on a restart, the infrastructure providers are like expecting these kind of things, and when it just happens randomly in some edge cases, on addition to that, it's not like something new that they have to suddenly learn. Like,
yes,
when you restart, don't you when you shut down, don't you save your fork choice?
We don't.
And then when you start back up, you load back what the view of the fork choice was before you shut down. Some clients are doing this.
So, but I believe it's implementation dependent, right?
Yeah.
No.
Like something like Koleshki is a bit problematic if you persist in fork choice. So having a way to clean up,
blow it out, yeah.
Especially like auto base to have these fake invalids in the shop, where like some concurrent debug or some database timeout treated as invalid block. And if you cache that and persist with it, yeah.
All right.
Earlier, my understanding of the view of the chain was that we have then confirmed, then justified, and then finalized.
Yeah, but ideally, yes.
But with this edge case of like reverting back to finalized, that means that a confirmed block can also be before justified.
Yes. Yeah, because justified can be unsafe, especially if you are doing a revert. Then you see it can only happen when something bad starts to happen in the network. So justified becomes unreliable as well. Likely can be unreliable.
But same applies to like confirmed block as well.
Yeah,
it can be reorged as the justified can be reorged.
Yeah, of course. I believe confirmed can be. Yeah. See.
Can confirmed be reorged without /sheets?
Like if you confirm something, then asynchrony starts to happen, right? So you confirm something, right? Asynchrony starts to happen, and no adversarial behavior detected, right?
Yes.
Yeah, I don't think it can be real. Because
it cannot be reorged without /sheet, or because like the penta was referring to adversarial, which means equivocation, right?
Not only equivocation, but adversary can move their balls from the
Not like suddenly switching to a different branches.
Yeah, exactly. After a new job starts, this can happen without slashing.
Okay.
Or adversary can do some other stuff like sending votes, splitting views, short split views can also kind of affect this.
And justify the reorg without slashing.
No.
Justified, I don't know, but theoretically I think it can, without the slashing.
I mean,
Like if you just it depends. So you can if there is 2/3 that voted on another checkpoint, right, on the conflicting to the justified one, it will be real. But
yeah,
how
or
this
like with
can happen?
inactivity penalties, I guess. You can also just wait until like everyone who justified the current one is a minority.
But like this can happen for 2/3 of the majority without double voting.
Without double justified can be ruled without double voting, right? But
And without waiting for 2 weeks. Like that's
yeah. But that's hard to imagine what conditions should be there to do that. If we have like 2/3 adversarial state, of course it can happen. Like but yeah, that's something. One case. Another case is on the mix of the asymphony and adversarial behavior. Like
yeah, that's interesting. So in a way, this is just a better, like the current justified that we put as safe, we probably should never have done as safe.
yeah,
It should have been finalized because we're selling justified as safe right now.
yeah, exactly.
Telling people, hey, just use this safe thing. It's an API.
Yeah,
It's called safe.
it's not
And
tell
we're
this to
losing
anyone.
this in the Indian API. as
Yeah.
well.
Because Solana will start to complain.
But it shows up on Ethernet and everywhere, right? And Solana, I think.
I don't think they. I don't know who used the safe. People exchanges, most of them they use just like some blocks, some key confirmation.
Yeah,
As in proof of work.
very scary as well. Like
Of
I've
course.
given it like 30 confirmations. They ignore
Yeah.
finality and everything.
They ignore justification either. So
Yeah, that's a good thing, I guess. But like
yeah.
Yeah.
All right, let's try to finish. Partial improvements, do reconfirmation in a more efficient way. So this is, as we said, more theoretical thing. We don't want to affect the algorithm run, but it requires more thinking and research. Beta failure mode for cases when block remains canonical. We have covered that pretty much.
Yeah.
And do late block handling. So for the late block handling, here are the numbers. If you use the same approach as for the empty slots handling, we can see the improvements. Where like in 2 slots we have 99.14% block confirmed, which is great. Yeah, numbers are quite appealing. But the problem with the late block is that we need a proof that the same approach would work and would be safe to use as we used for the empty slot. It's not yet done, and I don't know if it actually can be done. So it's a question.
Like late block meaning like some clients reorg late blocks in some situations,
Yeah.
like not in every situation. And other clients don't like which cases is late block.
Oh, just 50-50, like 50% of attestations come to the parent, 50% come to the block that come late. You are not going to reorg this one, right? Because the threshold is pretty high, but it affects the confirmation.
Or like if it's an epoch transition. Oh no, yeah.
Yeah, if it's an epoch transition, if it's
Yeah, then I think it never gets agreed.
Okay.
There are some cases there.
So late blocks are much more of frequent thing than the empty slot. Yeah. This is why it adds like, some more significant number to like in terms of improvement of the performance. All right, quality of service and API. So what to say here is basically this algorithm is not on the critical path of the core protocol. So it depends on the consumers of a client. Basically, if it runs for 1 second, probably it is fine. Maybe for the iteration of the algorithm, if it's not super optimized. But maybe some consumers, theoretically, I don't know how practical it is, but this algorithm can be run in the same slot, like in slot N to confirm block from the slot N after the attestation boundary, like at the aggregation boundary, because especially if it's a super node and it's subscribed to all attestation subnets, it can observe enough loads already to confirm a block, like not wait for the start of the next slot, but it can confirm it pretty fast, like in maybe 2 seconds or 4 seconds after the block was published. In this case, it definitely will have to be fast. So yeah, so the quality of service depends.
Just I guess maybe pedantic point. I don't know about this. The supernode as specified has nothing to do with attestation subnets. Wait, sorry. The supernode as specified has nothing to do with.
Oh no, I'm not like it's okay if a node is subscribed to all the attestation.
Yeah. That's all.
Yeah. Okay. That's right. For the nodes running validators, this algorithm can be disabled. Like they don't need it, So yeah, probably not. So if it's not fast enough, like if it incurs some additional load, disable. We're going to reuse the save block. Bear this in mind. This is already in the spec, and potentially, if it makes sense, we can incorporate confirmed block into Beacon API, similar to the finalized and execution optimistic flags. So this is confirmed. And yeah.
How often, because this is running on top of the protocol, and I also saw in the previous talk, I think from Devconnect 2 years ago.
Mm-hmm.
I think they ran some tests with a partner where they ran it through the debug for choice endpoint.
Mm-hmm.
So in principle, all the information is already there.
Yeah.
So we also probably don't need additional states. Because if they already ran it with the existing APIs. But I'm
not sure if this version can be, but maybe.
Yeah, maybe I was under the impression that there were situations where it was possible that you get the confirmation even faster than 12.
Yeah, exactly.
So
you can get that.
I guess it depends how frequently you called it. On after attestation processing. If that's the case, we also need an API that you can use to get notified when the save thing changes, because it's outside of the beacon block.
Yeah.
So either an event endpoint similar to the existing PORC one, or I think there is also an event for final.
Okay. Yeah.
I don't know.
I see.
But
this is something to think about.
That's missing from this list.
Huh?
That's missing from this list. So that's why I mentioned it.
Oh, you mean on the event stream is missing, or?
Yeah, like an event stream for.
Yeah.
In case it's more of.
Okay. And if we do something with the Beacon API, probably we can also expose some information if the confirmed block is stale, right? So it's I don't know.
Yeah, and also the block production process, also that the port join updated with payload attributes. Should the state block hash in the call be using this, or should we should we do this on attestation? On after attestation.
You mean on after update?
Yeah, right. Should we do on after update before from trying to build a payload, or what will happen?
So if you run it at the beginning of the slot, right, you will receive a block. You will update the fork choice and send this information to the.
For block production, I don't receive a block. I build a block.
All right. But you will receive it the previous block. Oh, you will run it. Yeah, I see.
I have to tell the EL in the previous block, hey, I'm going to build a block, please start building.
Yeah.
And then at the start of the next block,
Mhm.
probably I do the on after attestation thing, and then another FPU maybe, and then I do get payload, and then you payload and FPU, or
I don't know. I would not. Yeah, I see what I mean, but
yeah, like the block production flow is a bit out there.
yeah, but right. I think it's implementation dependent, and
It's EL, like it's spec dependent because the ELs are very strict about the order.
right. But the spec does not say when you should pass this information.
What is the confirmation will have to do with?
It's in the fork choice updated, which is the call to trigger.
Yeah, it's basically the API thing, right?
Notify for
Notify for, yeah, the fork choice updated call. It has the safe block hash now. This is how it passed to the EL. And in the case of block production, you will not do the fork choice update before you start producing the block, right?
Yeah, I mean that's what starts using.
Yeah.
we are sending justified block hash right now.
Yeah, we say
No,
say
finalized, safe,
Safe.
so to say, and had.
Justified.
Like
it's a
same is the
twofold.
justified.
Yeah. Safe is
It
justified.
probably doesn't matter what the hash is in. The EL doesn't do it.
Yeah, well,
Actually, yes, but I don't know how the safe block is used on the EL.
Yeah.
This is what probably exchanges will switch to, right? If they want to. All right, so yeah, this is the last one. Testing and delivery. We have two proof of concepts in Deco and Lighthouse. Prism has the implementation of an old version of the algorithm. So on the testing thing, yeah, there was some work, and this Deco and Lighthouse implementation are proof of concept use the most recent version of the algorithm. So the testing is just basically a straightforward and trivial thing to do, like trivial in terms of like the test format is basically extend the fork choice test format with this confirmed root property, so everyone can check it, right? As you said, we can run this on the node and get the proto-array coverage. We can potentially use model-based test generation approach, but we haven't think about it yet. This is like to generate a lot of tests to cover all these peculiarities and all these like execution path of the algorithm. Yeah, no hard fork required, obviously, because it's not on the critical path of the core protocol. Yeah, and that's basically it. On this, yeah, that'd be great to have it.
Thanks a lot for the
possible.
slides and
Yeah.
text.
Yeah, I hope it was not too boring.
No, it's very interesting. Like, I wonder why didn't we do this 2 years ago? Like, what was like? Is there any reason what was holding it back?
I don't know. Roberto, maybe a question to you. Why didn't we do it 2 years ago?
I don't know. Nobody seemed interested, so we do spend a bit of time on the security proofs, but yeah, but
We were waiting for proof for a while, and then also the PR just never got merged. Like the
Yeah.
consensus-based PR.
Yeah.
And the new PR is red, I think. Like
Yeah.
this doesn't pass tests.
Yeah, it's you mean it's red because not because it doesn't pass something, because the flow is broken.
Oh.
Because it should not check out the repository. Yeah, that's it's
Okay, so if it's ready, I can do it in Nimbus and
Do we have timeline for spec tests?
Huh?
Any timeline for spec tests?
Oh yeah, I forgot to mention we have one test as a proof of concept for testing,
Okay.
a test generator that we need to we will focus on the testing in December. Like this will be the main focus.
so I guess one point I would make is hard. I agree that the core of this is not hard fork dependent, which is good. And even in principle, things like the engine API modifications that are being discussed, or Beacon API, sort of course, don't in principle require hard fork. practically they've been synchronized to hard forks, typically when feasible. I don't know whether that makes sense. Is it worth trying to kind of, I mean, obviously there's a lot of approaches here. One is just kind of get these implemented, get the per se, the core, so to speak, of this implemented, and then address those next hard fork. Other parts, obviously, there's already precedent that Raul, and in a different context, I know, but is already looking at sort of this mid hard fork kind of update for his own purposes, and that we could pursue. So there's a lot of options, obviously, but
Yeah, maybe it can be tied to the. I don't know. I don't want to say that actually. I don't want to tie it to any hardware. So my personal preference would be to start working on this as soon as is possible, and just deliver as we have it, and we can probably when we see the preliminary delivery date, we can probably think about like doing it as with a hard fork or as a separate thing, because in this case there is no change to the API at all, except for the case where we would like to change the beacon API. I don't know what's the flow for changing the beacon API. Should it be tied to the hard fork? But I believe not.
No, you can just do normal minor release.
Mm.
Yeah, you just need to be.
Yeah, this one is probably like because it doesn't break everything that's existing. But maybe like the new response field, if it's like something like execution optimistic, that's a field in the response JSON. Maybe there is some parsing. If it's too strict and doesn't like extra fields that can break. But like in the request, like if you just add a new, like right now you can say like head or finalized or justified. I think just adding safe there is probably all right. But it's very hard for clients to discover what features are actually supported by a Beacon API server because they watched the versioning and it's like on a per request basis rather than per basis.
Using this safe block hash to notify the EL, and if some EL is working with say one CL client and then they switch to another CL client and that CL client does not have implemented this yet.
You cannot switch, like ELs are tied to a C. You cannot drive an EL from out. Like if we had setups where this happened and the dev guys just ignored all those issues. Like
well, it's not issues. They're not issues.
yeah, I mean, there were some issues, GitHub issues.
Sure.
And we had, I think we had this in the past where driving the same EL with multiple CLs to save resources.
Yes, but my point is that it's not a real thing.
No, that was just a question.
Okay.
What happens when you switch from one CL to another one?
Yeah. I don't think I do want to say this, like, as far as to follow up, I guess, on Ethan's point about the payload attribute version of FCU. One point is like some of these are, and they're not intrinsically tied to. I mean, you can put them wherever in the slot makes sense. Whether because you were talking about in terms of the synchrony assumptions that this should be right. It's actually important to not do it too late or too fine. That breaks a little bit. I mean, or it has to be, let's say, carefully engineered a little bit. If one, to the extent it starts interacting with these payload attribute FCUs, because in particular, there are cases, and I'm going to be a little more aggressive about always making sure it can do it at the end, near the end of a slot, but there are cases where you might want to wait into a slot, or reorgs happen, so it can't necessarily respect this. I mean, specifically that part, the payload attribute FCU is, let's say, tricky to make that respect the synchrony part of what you described before. I mean, it can cache the values, I guess.
Yeah, I see. So the synchrony part relates to those two variables. So you have to update them at the beginning of each slot. And the other part, when you call the algorithm, it basically not that tied to the slot boundary. And probably it makes sense to have a note about it in the spec, or spec it in a way that it will be clear that what has to be done at this boundary, what can be done at any point in the slope. So then you can basically outbreaking.
Yeah, I think that's a reasonable. I mean, about this for sure. I mean, I agree, but also more broadly because I think your presentation covered several of these cases actually where there's semi implicit assumptions maybe in the spec. Sometimes it's documented, and sometimes the paper, the spec does in fact just say you have to do this at this time, but sometimes there's it's inferred from how and it's probably useful to surface those assumptions.
Yeah, I see. Well, yeah, let's just figure this out
Should it be
in the PR.
like this reuse safe block? Given that safe currently isn't safe, should we like consider a new like maybe confirm?
We were considering this, but that's
Too much effort.
For almost no gain.
Is anyone using the current safe?
The current safe, we were trying to reach out. Maybe you guys know more, but we were trying to reach out. As far as I'm concerned, we were trying to reach out to different consumers, and I only heard from Arbitrum. They use safe because they know that it's the justified block. So they use actually the justified, but they call it. They obtain it by the safe tag.
So
and they.
So if they assume it's justified,
right, but they actually happy to switch to finalized once we have these.
Okay.
I believe they will use Prism anyway, and they will be aware of this change. And this is the only case we've heard back from.
Yeah, then we can reuse.
Yeah, I think it makes sense to reuse.
Why are they using just charge? If they're happy to, that's actually I was expecting to hear the other way around. Is like they'll be happy to switch to sort of safe if once that. But if they're happy to switch to the slower, more conservative version, why are they not doing that now? Like what? Like I don't understand the reasoning.
I don't know.
Okay.
Honestly.
Okay. Maybe sell your ARG tokens.
All right. Okay, guys. Actually, we are almost at the time, right?
Yeah.
I think I should stop sharing.
I don't know if anyone has a room, so I think we could prolong.
Roberto, do you want to add any or on any aspect?
No, I think you covered everything.
Is Aditya still working on this as well, or is it only Roberto and Francis?
Aditya has like moved on to different things. But yeah, I would say Roberto, Mikhail, and Luca are
Luca, sorry.
Yeah, and forgot to say that. Maybe it said, but there is a shorter explainer with the intuition. It's very good, so just read it. It's a very good, yeah. It goes into more details than the presentation.
Thank you so much for your time.
Thank you, guys. Any questions, any follow-ups, or should we just regroup later on the GitHub, collaborate on that?
Yeah, I mean, the spec tests, maybe Portus should review as well a little bit.
Right. Yeah, I was wondering kind of like the EPBS case, how does it like combine with the confirmation rule?
Yeah.
But basically, it should not be that difficult because the confirmation rule, it reasons about the beacon blocks, right? So it's basically, if the beacon block is confirmed, then the payload that is the ancestor of that beacon block is going to be confirmed. Like, yeah, I think.
Yeah.
I mean, I guess it changes. It makes things worse in that now you will not immediately, if you get like a one block confirmation, it's not going to confirm the payload. You're going to have to wait.
Yeah.
Yeah, that's the same with the same community actually.
Yeah, Francesca, can you see any problem with the fork choice, like the fork choice changes and we need to do deal? Okay, that's great. We have to do it. Okay.
Because like the fortress really just still runs on the regular attestations, and it's only like the decision at the tip around the payload that like about the last payload they might handle the PTC, but says this confirmation rule doesn't say anything. It's not going to say anything about the things that don't have actual votes, so the last payload. So I mean, basically, as long as you interpret a confirmation for beacon block B to not mean that the payload is also confirmed, then it's fine. Like it's more like how you consume this. Like you shouldn't take like B to be confirmed to mean that the payload potentially associated to B is confirmed. You should take to mean like what you said, the payload, the ancestor's payload is
Like the latest payload in the state.
yes.
Yeah.
So like if you interpret it this way, I think everything is fine. It's just like the UX gets or like the latency gets worse.
Yeah, at least on the spec level, I understand that, but probably there can be some implementation detail. It depends on how implementations will handle these changes in the BBS fork choice. I don't know. Yeah, but this is something just to keep in mind.
Yeah, just double check with both. I guess you need probably December to make tests nice and everything like that.
Yeah, but yeah, let's just start the discussion now, like on the PR. And
Yes.
it makes sense to start like doing some work also because this version of the algorithm is the one that we stick with. Any improvements further, we are not sure about the timeline when they come. So it makes sense to start working on it because this is a kind of stable target, stable version. So yeah, and testing, it just we'll work on this parallel.
I guess I have a broader question about the scope. This because you're referring to so this is the initial version, and obviously there can be improvements. And there were several points in your presentation where you noted there were kind of conservative assumptions, the revert to finality, and could go, etc. So in terms of, in particular, obviously improvements to the algorithm are always welcome, but at the point of also incorporating things into the API. So I guess what I'm wondering about is, as Ethan was getting at about like, does one add a field? Do you use save? Do you use like another angle there is exactly if the other aspects of the definition change. If we change the way that the revert finality works or doesn't, does that mean that except for the API issues, I guess, and there's more than the algorithmic issues, but to the extent that it starts being exposed to users already and fundamental behaviors change because of improvements.
Yeah, I see, but the only one thing is that we will have a more like a beta failure mode, right? This can change, but I think it's a strict improvement. It's just better than
sure. Yeah. Oh no, I mean I agree it's better than that.
Yeah, but we do not expect the changes which could make it worse. Like that's
okay. So
it should be forward compatible kind of thing.
Right. So it would be reasonable to take, even if we do add sort of API field values along those lines, just to continue to reuse those in improved ways because improvements.
Yeah.
Okay.
All right.
Yeah.
Thanks everyone. Thank you for we didn't do a break, but hope it's fine. All right.
Thank you, Mikhail, for the presentation.
All right. Bye, Roberto. Bye.
Bye.
Bye.